So the next talk is from Gilson, School of Mathematics, University of Glasgow, and she's going to talk about ultra-discrete equations in solid and gases.
Thank you very much. I'd first of all like to thank the organisers for inviting me. And I have to apologise a little bit for this talk is going to look, some people have heard something really very similar before, not so long ago here. So I apologise for anyone that's has to listen to similar things again. So yeah, I want to talk about the ultra-discrete KdV equation and its solutions, and relate this to Soliton gases. So I'm going to first of all start off with a very easy introduction to, well, just going to mention the KdV equation because the system I want to talk about is what's called an ultra-discrete version of the KdV equation. So this is something where you've discretized time and space, and in the original things you also discretize the so what's called like a box and ball system. So you have boxes, which are your space component, and then the balls are just either are moving along in boxes, and the balls are either a 1 for a ball, or if you've not got a ball in a box, you've got a 0. So you've just basically got two discrete dependent variables, but I want to generalize that to continuous dependent variables. And then I want to say a little bit about the solutions and then move on and try and relate this to Soliton gases. And it turns out, in terms of relating to Soliton gases, it's really quite straightforward in some ways, because you have, if you look at Soliton gases and the KdV equation, your solutions are much more complicated. The solutions here are very, very simple. Okay, so here's your KdV equation, which I'm guessing that everyone knows something of. And it just models shallow water equations. So the typical solution is a sec squared, the Soliton solution. So this is a single soliton. And as with a lot of the soliton equations, or practically all the soliton equations, the higher solutions with a larger height go at a faster speed. So that's very typical here. So the speed of this solution is 4 kappa squared, and it's got a height 2 kappa squared. So we can just move the solution along, moves constant speed. So what's a box and ball system? Well, I'm going to take a string of boxes and going from plus to minus infinity. And in the boxes, I'm going to put some balls. I'm going to assume I've got a finite number of balls. You don't have to assume I've got a finite number of balls, but there you have it. And then I'm going to evolve the system. Now, you could do this mathematically using a mathematical equation, or you can simply follow what's called evolve your boxes, your balls in the boxes. So I'm going to just write a second copy of the boxes and balls down, and I'm going to change them to a different colour. And then what I'm going to do is I'm going to come along from the left-hand side and start picking up the balls one at a time. And I'm going to pick them up. I don't know if you can see that well. So I'm going to pick up this ball, this ball, this ball, because that's all I can do as I pass by. So I'm going to pass in from left to right. Then when I get a space, I'm going to put the ball in space. And then I'm going to carry on, pick up the next balls and then put them into the space, and so on. So when I come along here, I get to a point where I've picked up the balls and I've put them all down. So I'm left holding nothing. So I've then got a space here. So I carry on doing this right across. So I scan right across, move the balls along to the next available space. And that's right. So then take away the remnants of the balls from the last flight. So this is my my first evolved step. So I carry on doing this. So this is time, starting with time step 0, then I have time step 1. So sort of mathematically, my empty boxes are zeros, my full boxes are ones, and so I can write my very top step as just a string of ones and zeros. And that's my second step. Okay, so generally, if I carry on evolving, this is a very simple case here. What you find is you get soliton-like behavior. And so here I've got a length 4 string of ones, and because it's a length 4, it moves speed 4. Here I've got a string of 3, and so it moves with speed 3, and here I've just got a single one which moves with the 1. If I evolve it, I find that they will all come together because of the different speeds, and in the middle I can't really tell what's happening. In fact, in this one it's fairly easy to see what's happening, but usually it wouldn't be. And then afterwards you see that this length 4 one has gone faster, and it comes out the other side, and it's still a length 4 soliton. And this is length 3 and the length 1. So the length 1 is phase shifted backwards, the smallest one. The length 4 is phase shifted forwards. So they behave just like solitons, but they're ultra-discrete. So the kind of thing that characterizes the solitons here is, as long as they're far enough away from some more ones, a string of, say, 4 ones followed by 4 zeros really is what represents a soliton of size 4. Okay. And you'll always get this behavior. If you go a long way back in time, you'll get the solitons with the fastest one furthest to the left. If you go a long way forward in time, you'll get to the fastest one to be furthest to the right. Okay. So this is the equation, and it dates back, it's quite old equation now, it dates back to 1990, the work of Takahashi and Satsuma. And so basically this is the next time step at some point N in the system, and all you do is you pick out the minimum of alpha. Alpha is the size of your box. Now, you don't have to have size 1. I've just showed you a very simple case initially, but you could have a larger box indeed in there. So you pick up the minimum of alpha minus the u at time step t, and this object here, which is a sum, and it's the sum of the u's at time step t up to n minus 1 minus the sum of the u's at time t plus 1 up to n minus 1. So this represents, this part here, in simplest terms, represents the carrier. So that's, if you imagine me walking along, picking up these balls, this is, and putting them down when I can, this is how many balls that I'm holding. Okay, so as I walk along, this is really just what I'm holding. Okay, the standard conditions were alpha's 1, so that's just a box of size 1. T and N are just integers, and U just takes the value 0 and 1. I'm more interested in the cases where U takes the value in the reals, and you could take alpha as a positive real, but you can scale things, so I can always really take alpha as equal to 1 without any loss of generality. Okay, so basically time and space are discrete, however my solutions can take any real value. Okay. I don't really want to spend time on the relationship with the KdV equation because it's not a lot of time, but basically you have the KdV equation, you can do a discretized version of the KdV equation. This gives me, well, here's my discrete version, and here's it rewritten in the way that I want. And then you do some rather strange limiting thing. So basically you take your quantities from the KdV equation, and so I'll call them little a and little b, and do set little a equal to e to the capital A over epsilon, and same for any of the variables you have. And then I take the whole equation, take epsilon times log of my equation, and then I let epsilon tend to 0. And that has the effect of basically changing multiplication of objects into addition, and addition of objects into maximals. Okay, so it gives a way to go from the maybe times plus to plus max. And this is where you obtain the ultra-discrete equations. So again, this is done back in 1996 by Takahashi and Satsuma. Okay, so let's not worry too much about the details. So I do that and I get my equation. So this is my equation again, in the form I want. So this part here is really the carrier, and this part here is the spare capacity in the particular box you're looking at. So if the spare capacity in the box at the next stage, you fill up the box as much as you can, unless you haven't got anything left in the carrier. Okay, so you can actually do this with use less than 0, and then you really do lose your box and ball interpretation, but you can do some rescaling. You can sort of move everything up and have a sort of background material, so you can kind of reinterpret things in a slightly different way and get rather slightly different structure box and ball things appearing. Okay, so so I say I'm interested in values that are not just 0 or 1. I'm going to keep my alpha to be 1, so I just a full box is 1, an empty box is 0, and I'm going to have so instead of really a sort of box and ball situation, I'm going to think of it as a box and liquid situation, so I can put as much stuff, or I'm not forced to stick with units of 1 for you. Okay, so in terms of evolution, again, I'm not going to say much here. We can ask questions, and they have been asked a long time in the past. Things like, if I give you an initial setup, how many solitons do we have, and how large are they? Where are they situated, etc. Well, you can answer all these questions. There's some very nice techniques for doing this. So I'm just going to show you a kind of example here where I've just got a set of 0s and 1s, and let me evolve this along in time. If you evolve it, you'll see the different solitons emerging out of here. And so this is the fastest one, it's a size 6. This is a size 3 that emerges, and this is a size, so let's just go back one. This is a size 2 soliton. These are size 1 solitons. Now, so this is a sort of significant difference between the KdV equation and this, is that you can have as many solitons of the same size as you like. If your solitons are the same size, they all move with the same speed. So all these ones here, it's all size 1, just move with the speed 1. So once you've got the other solitons that way, they're really very boring, but you can have as many as you like. So this sort of lends quite well to the idea of the soliton gas, that you don't have to worry about doing sort of finite gas solutions or anything. The solutions for the soliton gas are really exactly the same as your standard soliton.
So in the animation, you were moving the window because the soliton of the.
Oh, yeah. Yeah, no, I've time stepped back one every time so that these ones don't run off. Yeah, yes, sorry, I didn't say that. Yeah, so I'm moving backwards just to keep the size 1 stationary. Okay, so that's just a picture of it all put together. Okay, so one other useful thing to have is to sketch a profile of these things, because this gives you an idea of what solitons you have. So if every time I have a ball, I do a sort of cumulative plot of going up 1, and when I have all the ball, I go down 1, I can actually quickly see what sort of my soliton content is. So I look for small peaks, and they're all the single solitons of speed 1. Then I sort of ignore them. I can close, if I want, I can take them out and close up the gaps. But I'm not going to do that here. So I can then identify which of the next size solitons, and these are two size 3 solitons here, because they go up to 3, and then this one has a size 5 soliton. So just by sketching a sort of up and down diagram, I can very simply see what my soliton content is. And you can, in fact, if you want to evolve these systems, you can do it linearly. But what you have to do is it's a very clever technique that was developed by Tagai and Kagagi and some others, where you can actually, you take your small solitons out and you move, it's called rigging. So you deconstruct initially, you take the smallest solitons out of the system and you move everything backwards to take into account that they've gone. You then take out the next smallest ones and move everything backwards until you've got just the largest soliton left. In fact, take that out, but note where you've taken everything out from. When you've done that, your solitons are kind of separate from one another. Evolve them all according to their size separately, and then put them back in. You put them back in the right order, and you'll get them into the place they should be. So that's actually a very clever way of doing things. And the reason it works is if you imagine taking out the biggest solitons go the fastest. So if you imagine taking out the smallest first, that's and moving everything back. When you have the biggest ones are phase shifted forward by the smallest ones. So if you remove the smallest ones, and you're basically phase shifting everything else back, so as if the smallest ones weren't there. So you just basically keep taking things out, and you will get the correct answer when you evolve linearly, and then you put everything back in. Okay, so what I really wanted to talk about today was ultra-discrete soliton gases. So I'm going to assume I've got a random array. I can do this with non-integer size things. So this is a random array of solitons, so some size 1, some size 2, some size 3, and I'm going to just if you think about having this is just a blow up of the bit in the middle, and so if you want to work with a rarefied gas with not many solitons in it, that's fine, but you could work with something that's more solitons. And in fact, for the ultra-discrete situation, it doesn't really make any difference. Okay, and that's sort of just a blow up of what I've got. So just as a quick thing, if you want, what the sort of first thing that people look at is what is the actual, if I send a soliton through a field of solitons in my gas, what speed does it go? Well, because it's this is a large soliton, because it's phase shifted forwards by going past smaller solitons, it will go faster because these solitons are here than if there wasn't a soliton. So this is just going 8 steps, start with a soliton over here, end up with it over here. And if I didn't have anything in any small solitons, it would just shift less far. Okay, so the important thing here is what the phase shifts. Well, a soliton of size eta is phase shifted. If I take a soliton of size eta and it's bigger than the soliton of size mu, the soliton eta is phase shifted forward by 2. No, let's get this right. Yes, if mu is smaller than eta, my soliton is phase shifted forward by 2 mu. The bigger soliton is phase shifted forward by 2 mu. The smaller soliton is phase shifted backwards also by 2 mu. Okay. So if I have n solitons of size mu, and this soliton eta goes past them because it's bigger, it's phase shifted forward literally just by n times 2 nu. So the relationship's very, very easy. So what I want to do is define a density of solitons in a region. So I look at the region and I've got different size solitons in my region, lots of different sizes. They don't have to be integer in size. And then the density is just going to be basically the number in the region divided by the length of the region. So if I imagine I've got my soliton gas, it's got many different solitons of different sizes in it, and they have some density. So if I want to know the speed, the bigger solitons are obviously going to, with time, pass through the smaller solitons, so it's going to get phase shifted forwards. And so I can work out an apparent density just in terms of what happens to it due to the soliton of smaller size. I can work out the apparent density of the solitons in the gas from the point of view of the soliton eta, and that is just given by 1 minus v mu over v eta times the density of mu. So basically what I get is you can work out the speed of a test soliton, and it'll be given by this. So the speed of a test soliton is given by the, I call this the natural speed, which is if there is nothing else in the system. And then you've got 2 mu, which is your smaller soliton, that's your phase shift. Then you've got the density times the difference in the speed, so it's v eta minus mu mu. Obviously, your system, generally, you're going to have lots of solitons, so you actually need a sum in here over all the different possible solitons and speeds. Right, so I'm getting short of time, so let me, okay, so here I've not really done anything, but I've put indices on the mu j. So I'm now imagining that I have, I'm not thinking about test soliton, I'm thinking about being inside the system, and this is the velocity of solitons mu j in the system. Okay, so one thing, there's some work that I didn't know about last time I talked by, well, several authors, but particular Freud and Sasada, who have looked at these things, and they've taken this and rearranged it, because you can write your velocities of all your different solitons into, you can rearrange and write it in terms of basically a matrix times your velocities. Yeah, write it as a matrix times the velocity and set it equal to your initial velocity. So this is just this written in matrix form, and then solve for your velocities in terms of V0. So you can invert the matrix. The matrix is non-zero, so that's in theory easy to do, and they look at that in their paper. So what I've actually been looking at is really what happens in the case where we've got our solitons don't have to be discrete in size, they're continuous in size, they have to fit in boxes and balls. That means some in the boxes, so it means some of the boxes may be full, some of the boxes will have a small amount of material in them, but you can still do the same kind of behavior. So now I no longer have a sum, but I have an integral. My smallest solitons are size 1. If I have any objects that are smaller than size 1, they also move at speed 1, but they're not really solitons, they're like a sort of background material. So I can deal with the background material, but I'm just going to remove it. So I'm going to have some solid size 1 up to a maximum size. Okay. Also need a conservation of mass, which equation, which makes sense because if I've got material going into an area, it's got to match up with the material going out. Okay, so I've got some pictures here and I'll just go straight to the conclusions. I haven't really shown you very much about the things that go on, but you can basically set up an ultra-discrete Soliton gas. As I say, these people, Koiba and Sasada, have already done that and they have some of the results. So I'm looking at the case where you've got a continuous 5 solitons rather than the discrete ones they're looking at. And the behavior is very similar to a conventional soliton gas. And in fact, in the continuous case, it's sort of more conventional than the discrete case, because you've got integrals of densities. And so this just says I don't need to stick to binary values for the solutions. And also, I don't have in the papers, for the case of the nonlinear Schrodinger equation, you've got soliton gases that move in 2 directions, and for the KdV, ultra-discrete KdV, you don't have that because it's 1 direction. So I don't have a candidate for an ultra-discrete bidirectional version. So I'll stop there. Apologies for not actually giving you much more information than that. Okay.
Thank you. We can take time for a couple of questions. Martha?
Thanks. So is there a possibility of doing something like that for modified KDB?
Yes, I think so.
Some kind of, if I understand, it's some kind of result of some kind of tropicalization of the.
Yes, yeah. Yes, so I think you can tropicalize the modify KdV.
But would it be?
You should then be able to produce the same sort of idea. You could have densities of gases and start off with some density profiles for the different size things in it. Right.
So you anticipated my first question with your last point, but is there a multi-dimensional analog of this? I mean, multiple spatial dimensional analog of this ultra-discrete system? I'm imagining your strategy for iterating through the dimensions would affect it.
It's not. Yes, it's the way you iterate is very directly one directional. I mean, these things. I forgot what they're called. You do have the sort of like the automata things where you have, I forgot what they're called, sort of skaters and things in 2 dimensions. So they do exist, but I don't really think, I'm not sure that they are actually solitonic is the problem, I guess. So if you have these things, they maybe work as solitons on their own, but then can you actually get a whole gas of them? I don't know, but I suspect not.
Well, one more question. So at the beginning, I thought that it was going a little bit in a direction of TASEP, total symmetric exclusion principle process, where you have these balls and boxes, but it's stochastic. Is there some interplay that one can have in those?
So what's the TASEP?
So at each time, sorry, let me tell you, there is a probability that a box is moved, a ball is moved from one place to the next available one. If it is available, it's moved to the next to the right.
But with a probability.
With a certain probability, right?
So it moves to the next available one to the right with. I guess I guess it's related because you're still going to get this kind of behavior.
Well, because there is also some kind of evolution of the average shape.
Yes.
But now I can.
Yes.
Many of the techniques that I've seen here, they seem to overlap, but of course the result not, because it's a different, that one
It's-
is stochastic, this is not stochastic system. But
Yes.
maybe there's some interplay that one can.
Yeah, I think there will be, yes, because you still have this kind of behavior of if you're doing a probabilistic moving at things, then you will have sort of objects that are preserved, but they're going at a different speed.
Maybe in the interest of
Yeah.
time.
Yeah, sorry.
Continue the discussion over the coffee
Yeah,
break.
yeah.
Thank
Okay,
you
thank
for
you.